Hello friends. So today we are going to solve the questions from modern physics. And these questions are from the year 2021. And total we are going to solve 10 questions. And in these 10 questions, we are going to have 6 questions from the mains and 4 questions will be from the advance. And for the mains purpose, this is part 2. In the part 1 also, for the year 2021, we solved some of the mains questions. Okay, so in this we are going to solve 6 mains and 4 advanced. So the first question, the half-life of AU98 is 2.7 days. The activity of 1.5 milligram of AU98 if its atomic weight is 98 gram per mole is, and the value of Avogadro's number is given to us, and it is 10 raised to the power 23. So we have to find out the activity of 1.5 milligram of AU. Okay. So first of all, we are going to convert the mass which is given to us in moles, and from there we are going to find out the number of atoms. And then we are going to proceed further. So we start with converting mass into moles. So we can write that the number of moles is equal to small m divided by capital M. Small m is the mass which is given to us, and capital M is the molar mass. So small m is given to us as 150 milligram, so this will be 10 to the power minus 3, and the mass atomic weight is about 198. So from here we get that the number of moles will be 7.57 into 10 to the power minus 6 moles. Now we are going to find out number of atoms. Number of atoms, let us say it is represented by capital N, which will be equal to number of moles multiplied by Avogadro's number. So we simply substitute, we get the capital N, number of moles is our 7.57 into 10 to the power minus 6 multiplied by 6 into 10 to the power 23. And this gives us 4.54 into 10 to the power 18 atoms. And we are given that half-life is given to us, that is 2.7 days. So we are going to convert this half-life from days into seconds, then we are going to find out our decay constant. Okay. Or let's write the formula directly for the decay constant. We know our decay constant, that is lambda is equal to natural log of 2 divided by t half, and therefore we can write that lambda will be equal to natural log of 2 and our T half will be equal to 2.7 multiplied by 24 hours, and then it comes as a 3600 second per hour. So from here we can say that a value of lambda, that is our decay constant, is approximately as 2.9 into 10 to the power minus 6 per second. Now from here we can find out our activity, because we know our number of atoms and we know our decay constant. Therefore we can say activity, that is our A, is lambda multiplied by our n, and lambda is our 2.9 into 10 to the power minus 6, and our n is 4.54 into 10 to the power 18. So from here we get our activity, that is our A, and that will be equal to 1.349 into 10 to the power 13 disintegration per second. And this activity we can convert into Curie. So we are going to get this as 1.349 into 10 to the power 13 divided by 3.7 into 10 to the power 10, which will be giving us approximately 364.6 Ci. And so the closest is our option number 2, that is 357. So we can say option 2 is correct. Next question. It states that calculate the time interval between 33% decay and 67 decay if the half-life of the substance is 20 minutes. So we are given half-life and we have to find out the time represents 33% and 67% decay. So we start with our, that is given as half-life. So we are given as T half, which is our 20 minutes, and we are given as 30% decay. So we can write this as, if there is 30% decay, so which basically means that 67% of sample is not decayed. Okay, so we can say 60% of sample remains. So from here we can write that the ratio of our n upon n naught will be equal to 0.67. So where n is after some time t and n naught is our initial sample. So their ratio will be equal to 0.67 because 67% of sample is remaining. This is in the first case, and for the second case it says that 67% decays, 67% decay, which means 33% remains. So in this case the ratio of n upon n naught will be equal to 0.33, and we know that our decay constant is our lambda, and we can write that our decay constant lambda is equal to natural log of 2 divided by t half, which gives us 0.693. T half is given to us as 20 minutes, so this comes as 0.034 per minute. And now we have two values of n upon n naught. One is 0.67, another one is 0.33. Okay, and let's find out one by one for each. So we start with the 67%. So we can say for 67%, we can write that our n upon n naught is equal to e raised to power minus lambda t1, and this value is our 0.67. And let me write, this comes as e raised to power minus lambda t1 is equal to 0.67. So if we take natural log both sides, we get this as minus lambda t1 is equal to natural log of 0.67. And lambda we already know, and so we can say that our t1 will be equal to natural log of, this comes as minus 0.4, and lambda we calculated as 0.034, and this is also negative. So we get from here that our t1 will be approximately equal to 11.55 minutes. Similarly, we are going to solve it for remaining is our 33%. So we can say for 33%, once again we have our n upon n naught is equal to e raised to power minus lambda t2, and this is equal to 0.33. And taking natural log both sides, we get this as minus lambda t2 is equal to natural log of 0.33, which gives us that t2, we have this as minus 1.108, and this is minus 0.034. This gives us the value of t2 is close to 31.99 minutes. We got the value of t1 and t2. We need to find out their difference. Therefore, we can say difference, whichever delta t is equal to t2 minus t1. We get this as 31.99 minus 11.55, approximately equal to 20.44 minutes. And option number 2 is correct. We can just approximate equal to 20 minutes. So we can say option 2 is correct. Next question. It states that a radioactive sample disintegrated via two independent decay processes having half-lives as T1 half and T2 half respectively. the effective half-life of T half of the nuclei is. So we are having one sample which disintegrate independently. Okay, so this is keyword here, independently, because then only we can use the effective, you can say, decay constant formula, which will be equal to lambda 1 plus lambda 2 for first half lambda 1 and for second half lambda 2. This is only possible when both are decaying are independent of each other. So we are having, you can say, two half-lives. So let us call first process as mode 1, and in this case the half-life is, let us suppose, T1 half, and the corresponding decay constant is suppose lambda 1, and we have mode 2, and the half-life is T2 half, and the decay constant is lambda 2. And for each mode we can write the formula that our lambda 1 will be equal to natural log of 2 T1, and lambda 2 is equal to natural log of 2 and T2 half. Now they are independent processes, therefore we can say that effective decay constant that is our lambda effective will be equal to first mode decay constant and second mode decay constant, because they are independent processes. Now we simply, okay, and we are also given that the effective half-life is T half. Therefore from here we can write that our lambda effective will be equal to natural log of 2 divided by T half. And from here we can say that our T half will be equal to natural log of 2 divided by lambda effective, which comes as natural log of 2 lambda 1 plus lambda 2. Now we can just substitute value of lambda 1 lambda 2. We get this as T half will be equal to natural log of 2, and this comes as natural log of 2 for first mode, and then we have natural log of 2 for second mode. And this natural log cancels out throughout, and this will be giving us, we take the LCM, and this comes as first half second half divided by first half plus second half. So therefore we are having option number 3 is correct. 3 is correct. Next question. It states that a plane EM wave of frequency 500 MHz is traveling in vacuum along y direction at a particular point in space time. B is equal to 8 into 10 to the power minus 8 z unit vector. The value of electric field at this point is, so we have to find out the magnitude as well as the direction. And we are given that the wave is traveling along y unit direction. So you can say that direction of wave let us call this as y unit vector. Magnitude we can just easily calculate because that is only with respect to the magnitude of magnetic field and multiply by speed of light. So we can say that electric field which is our E is equal to C multiplied by B. In this case, because it is traveling in vacuum, therefore we are going to multiply it by C. Otherwise, we have to find out the value of the velocity of light. And this comes as 3 into 10 to the power 8. And magnetic field magnitude is our 8 into 10 to the power minus 8. Therefore, we get that the magnitude of electric field is equal to 24 volt per meter. So the option possibility is first and third is the correct one. Second and fourth are wrong. We are going to find out whether it will be negative x-axis or positive x-axis. Okay, for that we are going to use that all there are three components: electric field, magnetic field, and the propagation vector are perpendicular to each other. Okay, wave vector, sorry, not propagation vector. And we are given that the direction of wave is our y unit vector, which is nothing but our direction of our this wave vector. Okay, so let me write it here. We have our wave vector that is our k, it is along y unit direction, and magnetic field is along z unit direction. Okay, so you can say that our magnetic field B, it is along z unit vector, and we know that for EM wave, electric field is perpendicular to magnetic field and is perpendicular to our wave vector, and our E cross B is in the direction of wave propagation. In the direction of wave propagation. So we can say that our E cross B so we are going to find out E cross B, and we can take, you can say, both values of E. One time we can take plus x, another time we can take as minus x. Okay. So first of all, let us assume that our electric field is along positive x unit direction. Therefore, we get our x unit multiplied by magnetic field is our z unit, and their cross product is going to be negative y direction, but this is given as a plus y direction, so this value of direction of electric field will be wrong. So this direction is wrong. Similarly, now we can just plug in that of electric field is along negative x direction. Therefore, we get minus x unit vector cross product z unit vector. This will be giving us plus y unit vector, and this is true because we know wave vector is represented as plus y. So the direction of electric field is our minus of x unit vector. Therefore, we can write magnitude is electric field is equal to 24 and minus x unit vector volt per meter. So we have option number 1 is correct. Correct. Next question. It says that the electric field intensity produced by radiation coming from 100-watt bulb at a distance of 3 meter is E. The electric field intensity produced by the radiation coming from 60 watt at a same distance is square root of x upon 5 times E, where the value of x is. So we have to find out the value of x. So we start with the relation between the power and electric field amplitude, or in terms of intensity we can say. So we can say that intensity of radiation from a point source that is of I is equal to P divided by 4 pi r square. And for a EM wave in vacuum, we also know relationship between the intensity as well as the electric field. So we can say for EM wave in vacuum, our intensity is equal to 1 by 2 C epsilon naught E square. Therefore, if we combine these two formulas, we can write in terms of proportionality that our electric field is proportional to square root of I, and it is proportional to our P upon r square. And in this particular question, we are given that the distance is same. So r is same. Therefore, if r is same, we can say that of electric field is proportional to square root of P. And we have to find out the, so their ratio is, in terms of E it is given, so it's quite easy now. And first it is given as a 100-watt bulb. Therefore, we can say that for 100-watt bulb, so it is 100-watt bulb. Let us call this as E100, which will be proportional to square root of power, in this case is 100 also. Let me write this as P100, which is proportional to square root of 100, giving us 10. And next is our, for 60-watt bulb, we get this as our A60 is proportional to P60 proportional to square root of 60. Okay. And we are also given that at 3 meter this is given as E. At the same distance for 60 it is given as square root of this is complete square root E. Okay. So let me rewrite it again. So I'm given that for our E100 is nothing but equal to E, which is equal to 10, and my E60 is given as square root of x upon 5 times E. And therefore, because this is the given relationship, okay, and this is also given. In this case, as the 100 watt energy is given as E. Okay, so we can just slightly modify it. We can write our E60 upon E will be equal to square root of x upon 5, and this will be our E60 upon E100, giving us square root of 60, and let us get square root of 100 because on the left side we have square root. Now it is quite easy to solve. So we can write this as x upon 5 is equal to square root of 60 upon 100. This gives us that x upon 5 is equal to 60 upon 100, and this 100 goes by 20, and 20 this goes by 3. Therefore we get that the value of x is equal to 3. So value of x is 3. Next question. It states that a plane EM wave propagating along y direction can have following pair of electric field and magnetic field components. So we have to find out if the wave is propagating along y direction, what will be the combination of our electric field as well as the magnetic field. So we are given wave vector direction, that is the direction of our propagating wave. So we can say that wave vector which is represented as k gives direction of propagation, gives direction of propagation, and we can say that this k is our y unit vector, and our electric field will be perpendicular to this k unit vector, and magnetic field will be perpendicular to the both. Or in the shorter format, we can write that our electric field is perpendicular to our y unit vector, our magnetic field will be also perpendicular to the y unit vector, and our electric field is also perpendicular to our magnetic field. Okay, so this is universal about the EM wave. So now we have to find out the possible combinations. So we can say not combination but orientations. We can say possible orientations, and we can say that if our electric field is along x unit vector, and which implies we can write this as E of x. Then our magnetic field has to be rather along z unit vector, or we can write this as our B of z, because this is going to satisfy that our wave is going to propagate along y unit direction. And secondly, we can also say that if our electric field is along z unit vector, so we can write this as E of z, then our magnetic field will be along x unit vector, or we can say this is B of x. So these only two possibilities are with respect to our electric field, because electric field cannot be in y direction because wave is propagating along y direction. Okay. So if we check the options also, from here also we can just make a wild guess that electric field in y is not possible. So therefore option 1 and 2 goes away, and magnetic field will here also we have electric field in y direction, so this is also not possible. So only possible is option number 3. So you can say that option 3 is correct. 3 is correct. Next question. So this question was asked in the advanced part. Previously all the questions were from the mains. And in this question, a heavy nuclei N at rest undergoes fission in P plus Q, where P and Q are two lighter nuclei. Let delta is equal to m of n minus m of P minus m of Q, where m, Q and m, n are the masses of P, Q and n respectively. EP and EQ are the kinetic energy of P and Q respectively. The speeds of P and Q are Vp and Vq respectively. If c is the speed of light, which of the following statements is or are correct? In this case, we have to remember that the heavy nuclei initially is at rest. So we can first of all going to use the conservation of momentum. Okay. So we can say momentum conservation, and we can write that our momentum of P plus momentum of Q will be equal to our momentum of N. But initially this N is at rest, therefore we can say that momentum of P plus momentum of Q will be equal to 0, and this can be written as that our momentum of P is equal to minus of momentum of Q. And momentum we can write in terms of our mass and velocity. We can say mass of P, velocity of P is equal to minus mass of Q and velocity of Q. And this negative sign only signify the direction. So for simplicity, we can just ignore them. We can say velocity of Q is equal to our mass of P mass of q divided by multiplied by velocity of p. And so, okay, we can check the option number C. So let me write it in the correct form. Solution is given as velocity of p upon velocity of q will be equal to mass of q divided by mass of p. Okay. So we have that option number C is correct. C is correct. Now let us consider the kinetic energy part. So you can say total kinetic energy. Kinetic energy, we can write our kinetic energy of P plus kinetic energy of Q will be equal to our delta into C square. Okay, this is basically you can say from mass defect. Okay, let me total kinetic energy from mass defect, and in this particular case this delta is the representation of our mass defect. Okay, because in the question it is given that a delta is equal to the difference between their masses. I am not sure whether m and okay, no, this is correct because usually we write it like this. Okay. So let us use the formula that our kinetic energy of P will be equal to our half mass of P velocity of P square. Kinetic energy of Q will be equal to our half mass of P and velocity of our Q. And we also know that our VQ is equal to this particular relationship. Therefore, we can write that our EQ will be equal to our half mass of MP, and VQ we can write this as mass of P mass of Q multiplied by velocity of P and its whole square, and this gives us our half. We have this as, sorry, this should be Q. This is Q and this is also here Q. So we can write that MP square divided by MQ, and this comes as VP square. Now we substitute that our EP plus EQ will be equal to half MP VP square plus half MP square MQ and VP square, and this entire summation is equal to delta C square. So on the left side we can just make slight adjustment. We can take as a half as common, and let us take MQ as LCM. So this is MQ, and in this will be coming as, you can say MP as common, and this will be coming as our MP plus MQ, and this is our VP square is equal to delta C square. Now we can just solve it for VP. and from here we get that our Vp square will be equal to twice mass of Q, and we have this as delta C square divided by mp plus mq. Therefore, our kinetic energy EP, we can write that our EP is equal to over half mp Vp square, and this will be equal to over half mp. We substitute Vp square, we get this as twice mq delta C square divided by mp, and this comes as mp plus mq. Here half and half, mp and mp cancel out, and this comes as our mq divided by mp plus mq multiplied by delta C square. Now we can find out our EQ is equal to, and this was our half mq and vq square, and that also will be coming as our mp plus mq multiplied by delta C square. So if we add them, we get that our EP plus EQ, and we can see that, let me write it first, we have our mq divided by mp plus mq plus mp divided by mp plus mq, and delta C square will be common. So this entire term will be equal to 1. So their solution will be equal to delta C square. Therefore, we can write that EP plus EQ is equal to delta C square. So we have option A is correct. A is correct. And next we have to find out the magnitude of momentum for P as well as Q. Okay. So magnitude of momentum, we know that is a product of mass and velocity. So we can say magnitude of momentum. Let us calculate for P, same we can calculate for Q also. So we can say momentum for P will be equal to mass of P, velocity of P. So we have mass of P and velocity of P, the formula we already know is our twice mq delta C square divided by mp plus mq. C we can take outside the square root, and mp we can move inside. So from here we get the momentum of P will be equal to C square root of twice, this will be coming as mp mq divided by mp plus mq multiplied by delta. And one second. Okay, we are given that mu is equal to. So this can be written as c square root of 2 mu delta, and similarly we can say that momentum of q will be also equal to c 2 mu delta, which is equal to momentum of p. So we have option number D is also correct. D is correct. Now we are left with only option C, that energy and their relationship. Okay. And I think we already found out that relationship, that our EP, energy at P, is okay. Here in this case, in this particular option, it is mentioned that energy of P will be equal to mp plus mp upon mp plus, one second, I think we calculated it. Yes, so this is our mp. Okay, so from here we can see that our numerator in this energy of P is our mq, whereas here it is mentioned as mp. So this option is incorrect. Okay, so from here we can say option C is incorrect. Next question. It states that in a photoemission experiment, the maximum kinetic energies of photoelectrons from metals P, Q and R are EP, EQ and ER respectively. They are related by EP is equal to twice of EQ is equal to twice of ER. In this experiment, same source of monochromatic light is used for metals P and Q, while a different source of monochromatic light is used for metal R. The work function of metals P, Q and R are 4, 4.5 and 5.5 respectively. The energy of incident photon used for metal R in electron volt is. So in this case, we have to remember that the P and Q are having a same source and R is having a different source. So we are going to start with the photoelectric equation and then move forward. So we can say that photoelectric equation, which gives us that our maximum kinetic energy will be equal to hc upon lambda minus phi, where phi is the work function and hc upon lambda is nothing but our, you can say, photon energy. So let me write it here. hc upon lambda is the representation of photon energy. So we are given that, or let me write this in the form of frequency also. We can write that maximum kinetic energy will be equal to h nu minus phi, where nu is the frequency. So we are given that both P and Q are having same source. You can say P and Q have same source, and let us suppose that source of light is having a frequency as nu1. Therefore, we can write the equation that our EP will be equal to H multiplied by nu1 minus work function for P, and our EQ will be equal to H nu1 minus work function for Q. And we are given that EP is twice of EQ. So we are given that our EP is equal to twice of EQ. We substitute, we get this as H nu1 minus phi of P is equal to our H nu1 minus phi of Q and whole multiplied by 2. So we get this will be equal to our H nu1. So this will be twice H nu1 giving a H nu1 equal to, we have this as 2 phi p. One second, this will be our twice of phi q minus phi p, and phi q is our 4.5. So this comes as twice into 4.5 minus 4, that is 9 minus 5, sorry, 9 minus 4, and this is equal to 5. So in the first case we get H nu1 is equal to 5, and or electron volt, this is basically energy. And from here now we can easily find out our EP and EQ, because this is simplistic of the formula. Therefore we can say that our EP will be equal to phi minus first is our phi of P, work function of P is our 4, giving us 1 electron volt, and we have our E of Q is equal to phi minus 4.5, giving us 0.5 electron volt. And we are also given that our ER is equal to twice of ER is EP. So from here we can say that our ER is equal to EP by 2, which gives us 0.5 electron volt. And we can use photoelectric equation for our R now. So we can say that for R, our maximum kinetic energy for R is equal to H nu2 minus work function for R, and all the values we know except for the work function part. So E of R is our 0.5, and H nu2, okay, H nu2 minus work function of 5 is our 5. This gives us that H nu2 will be equal to 5.5, sorry, 5.5 is 6 electron volt. And this is the our energy of incident photon is our 6 electron volt. Next question. It states that a heavy nucleus Q of half-life 20 minutes undergo alpha decay with probability of 60% and beta decay with a probability of 40%. Initially, the number of Q nuclei is 1000. The number of alpha decays of Q in the first R is. So in this case, we are given half-life of Q and the probability of alpha decay as well as our beta decay. So we can say our half-life of Q is given to us, that is 20 minutes, and alpha decay probability is given to us as 60%, and beta decay is given as 40%. Time interval is our 1 hour. So we can say T is equal to our 1 hour, or we can write this as 60 minutes. So first of all, we are going to find out our decay constant, that is our lambda. Therefore, we can say our decay constant that is our lambda is equal to natural log of 2 and half-life of Q, which gives us 0.693 divided by 20. So from here we get that our lambda is equal to 0.034 per minute. And we have to find out our total decays in time t. So we can write that total decay in time t, we can write that formula, that is our n decay will be equal to our n naught 1 minus e raised to power minus lambda t. And one second, this is with respect to Q. So we are given n naught is given to us as 1000. 1 minus e raised to power lambda we found out is our 0.34 multiplied by 60 minutes, and this gives us that our n decay is approximately equal to 875. So this is our in 1 hour. Now we have to find out our number of alpha decay in first hour, and probability is given to us as 60%. Therefore you can say number of alpha decays will be equal to 60% of total decay. And from here we get number of alpha decay is equal to 0.6 multiplied by 875, approximately equal to 525. So therefore option number D is correct. Next question. It says that which of the following statements is or are correct about the spectrum of hydrogen atom? So basically it is about two series. Balmer series and Paschen series, three series rather, and Lehman series. Okay. So first of all, we are going to find out the ratio of the longest wavelength for longest to shortest for Balmer series. Okay. So we can say for Balmer series, our value of n1 is equal to 2. Okay. And value of n2 will be 3, 4, 5 and so on. Therefore, we can write that our 1 upon lambda is equal to our Rydberg formula 1 upon 2 square minus 1 upon n2 square, and our n2 will be equal to 3, 4, 5 and so on. But we are interested in longest wavelength. Therefore, we can say for longest wavelength, let me write is lambda bs, Balmer series. So you can say for longest wavelength, the value of n2 will be equal to 3. Okay. And if we want to, we can also calculate by using the nth energy level formula, which gives us minus 13.6 divided by n square. Okay. Based on this, we can also find out the energy level at 3, 4 and 5 and subtract it for 2. Then also we can find out that value of n2 is equal to 3. Therefore, we can say that 1 upon lambda for Balmer series, and this is our longest wavelength. Longest will be equal to R 1 upon 4 minus 1 upon 9, and this gives us 5R upon 36, and we can say that lambda bs for our longest will be equal to 36 upon 5R, and shortest, our n2 will be equal to infinity. So for shortest, our n2 is infinity. So if we can just directly write that our lambda Balmer series shortest will be equal to 4 upon R. We can just find out the ratio now. So we can say ratio, we have our lambda Balmer series longest, lambda Balmer series shortest, which will be equal to 36 upon 5R and 4 upon R. R and R goes away, and we get this as 36 upon 5 multiplied by 1 upon 4, and this gives us 9 upon 5. So option A is correct. Is correct. Next is with respect to overlaps, Lehman series. This overlap is based on general concept. Okay. So we can just find out that later on also. Let's try to solve part C. So we have our for Lyman series, our n1 is equal to 1. Therefore, we can write that 1 upon lambda Lyman series will be equal to r 1 upon 1 square minus 1 upon n2 square. And we have to find out the shortest. Yeah, shortest. Therefore, we can say shortest wavelength will be giving us that the value of n2 is infinity. And in this particular question, it is given that lambda naught is actually the shortest wavelength for Lyman series. Therefore, for shortest wavelength, n2 is infinity, and we can just substitute. We get this as 1 upon lambda ls will be equal to r and from here we can say our lambda shortest is equal to 1 upon r, but the given is given as lambda naught, and this is shortest. This is also shortest. But the actual wavelength, lambda for lambda ls, you can say actual wavelength is equal to our lambda ls is equal to, we can just take the LCM, and this will be coming as 1 upon r 1 minus 1 upon n2 square, and 1 upon r is nothing but equal to lambda naught. Therefore, we can write that the lambda ls will be equal to lambda naught, and we can take n2 as LCM, so this becomes n2 square divided by n2 square minus 1. Okay. And the given formula is our 1 upon 1 plus m square. Okay, let me write it out. So we are given that 1 plus 1 upon m square times lambda naught. And even if we make 1:1 comparison, so from here we can say that lambda square is 1 minus 1 upon n2 square is not equal to 1 plus 1 upon m square. Sorry, here it has to be 1. So therefore, option C is incorrect. C is incorrect. Okay. And for the overlap series, this is based on the basic concept that our Balmer series is around about 400 nanometer to 700 nanometer. Okay. So Balmer and Lyman is with respect to our from 100 to 121 nanometer. Therefore, the Balmer and Lyman do not overlap. Okay. So we are having the option D is correct, and for Paschen is, you can say, greater than 800. Okay. So we can say that this option B is also incorrect. So both are not overlapping, but here it is mentioned overlap and here it is mentioned do not overlap. So option D is correct. So this completes the 10 questions for the year 2021. Out of this, 6 questions from the mains and 4 questions were from the advance. So this completes all the 10 questions from the year 2021. Thank you.